usual business to, again, be available for those that may need to talk to me about anything having to do with midterm, but we're also at the point of talking final exam. So as I said to you all, whenever we got together last, Monday, as I said to you all, I promised you I would be ready to talk about the final exam today, and I am. So here's the short story on that. We're going to do pretty much the same thing that we did with the midterm. I haven't written it though yet. I'm working on it, all right? And I expect that I'll have that wrapped up. I'd like to have it wrapped up today, but I don't know if I'm going to be able to get it today or it's going to be tonight, folks. I just simply don't know. But as soon as I get it done, I'll get it posted. It'll be available to you. Again, I think it'll be sometime tonight, all right, just so y'all know. And then the play there is going to be the same as we did with the midterm, with a couple of exceptions. First of all, we have one more meeting of this class on Monday, right? That's our last meeting, if I got the schedule right. I want to make sure that everybody downloads a copy of the final exam and is ready to talk about it on Monday, to ask questions, be prepared. I don't want any scenarios where anybody's waiting until the day it's due to download the final exam. That happened on the midterm exam. I know of only one case, but I suspect there might have been more. But I had one individual who didn't even download the exam until it was no longer available. So we don't want to do that, folks. That is, nothing signals, boy, I don't want to do well more than that. So I want to make sure everybody gets a copy of it. Get your own copy. Let's talk about it on Monday so that we can discuss the problems that will be on that exam. Unlike the midterm, there's not going to be a certain opportunity to ask questions beyond that other than the email questions, and we know those can go well and they can go less than well, but we want those. But I certainly want those. If you have questions, oh my gosh, email me. I'm just saying I don't know if there's going to be an opportunity to meet in person. At the same time, there isn't going to be a clear opportunity to have you turn that in as a hard copy. So what I'm going to be looking for on the final is a copy emailed to me. Now there's going to be questions of like, hey, is there a mechanism to send this to you on Blackboard? No, there will not be. What I'm going to be looking for you to do is to make a PDF of your exam or take a phone picture of it if that works for you, works for me, and send that to me. The only thing I want you to make sure though to realize, folks, is if you have 6 pages of stuff and you take 6 photographs and all 3 megabytes big, then sending those in email is not really a beautiful way to do it. Maybe you can make a less memory intense version of that. And I only say that because the Kettering server does a really crappy job of downloading those pictures when that's the case. So it makes it a little bit harder to grade it. So I'll want you to send that to me via email. The question is always, well, when is it due? So you're going to have it as early as today. Like I said, tonight, right? I want it to me no later than the end of the semester, which technically ends at the end of the final exam period, which is what? Next Saturday at noon or thereabouts. So it's got to be turned in by that time, by noon then. If you get it to me early, fantastic, good job. But if if you got stuff going on, you can't quite get to it until then, send it then or by that time. The only word of caution I'll give you though is, and it should be inherently obvious, the longer you wait, the less likely it will be that I'll be able to help you if you get hung up on something. So my so strong advice to you all is once you get it, start working on it right away. Get this thing knocked out, and that way if there's issues, we can deal with them. But the longer you wait, the less we'll be able to deal with any issues, all right? So, and of course, again, if you turn it in at 11:58 on Saturday morning and it's all messed up, there's not a thing I can do about it after that. So, I hope that message comes through clear. To put it in like 4 words, don't wait too long. Get it done. As far as the problems go, here's where it's going to get interesting. There are 3 problems on the exam that are going to be for everybody, no matter what. That will be a centroid problem. And let me remind you, when you do the centroid problem, don't draw an integral on your paper. If you do, you are doing the wrong thing. Use the table method, all right? There's going to be a centroid problem, there's going to be a distributed load problem, and there's going to be a friction problem. So the stuff we've covered since the midterm, Chapter 5, Chapter 6, those 3 problems will be there. But there are also going to be 3 additional problems, and those problems are specifically for those that struggle with the midterm. So in other words, there will be 3 more problems on the document. One, of course, will be a free body diagram type problem, one will be a machines problem, and one will be whatever else we did on the midterm, I don't even recall. Truss problem, right? To be as clear as I possibly can, if you did well on those problems on the midterm, you don't do those problems. You only have 3 problems to work on. That's it. Those are only there for those folks who did not do well. And I want to be crystal clear, and I got to be honest with you, I haven't thought this one out yet. But a lot of you that were dealing with some issues on the midterm have been talking with me, which is so smart of you to do. And we're trying to work it out so that we can help fix that problem. It will be necessary, and again, I'm literally thinking this out as I say it. I'm only offering the remedy for those problems to those individuals who had trouble on the midterm and have approached me to work with me on that problem. So in other words, if you had trouble on the midterm, you haven't talked with me, I'm not going to accept any work on the final exam. You have basically screwed yourself. So I'm probably going to want to make a checklist for my purposes of who has talked with me and who has been doing the work to fix this versus who hasn't. And of course, I know I'm setting myself up for an issue there because there's always going to be the argument, but I have been talking with you. Yeah, sure, right, okay, well, maybe I'm not remembering, maybe I am, I don't know. But the point of it is, if you have been talking with me, you want to make absolutely certain that I have checked you off or you're on my list so that I will grade your final exam extra problems. And even to be clear on that, let's say you're an individual who on the midterm kicked butt on problem 1, problem 2, but you messed up problem 3. That was the truss problem, right, in the midterm. If that's the case, then you're only working the truss problem in the final exam. You're not reworking the whole thing. In other words, if you've got any one of the conceptual problems right, then there's no need to rework any of that. It's possible somebody might want to know, well, hey, I did good on the problems on the midterm, but are you saying I can do better? No, to be clear, only if you scored a less than a 3 on a problem on the midterm. If you did a 3, you did good. Okay, you did good. And for those individuals who are reworking those problems on the final, 3 is the max you're going to get. So 3 is the max no matter what, and that's why it doesn't make any sense to have anybody who did a 3 or better try to score something better than that. So I think that covers everything that I can think of in terms of the final exam. How about you guys? Does anybody have any questions at all about something that I may have forgotten to cover? Anything? Anybody? Yeah, what you thinking?
Is it same with the midterm? Work on it with whoever.
Yeah, and again, I want to be, I want to talk about, thank you for bringing that up. I want to talk about that. Again, I encourage everybody to collaborate, with the intent being that if you don't understand something, learn from each other, teach each other. And that, by the way, tends to go really well. I had a few instances where folks reached out to me during the midterm and said, hey, I'm working with so-and-so, but he sees it this way and I'm seeing it a different way. Help clarify for us. My gosh, you guys have no idea what music that is to my ears, because that says we're trying to figure this out. We care, we want to learn. That is like, it just doesn't get any better than that. If you're one of those individuals that reached out to me and you want a letter of recommendation in the future, oh boy, let me know. I'll be so happy to send you one. But then it goes the other way too. It's like, hey, I worked with individual one, individual two, and we all had no clue. So guess what? We all got the answer totally wrong the same way. That's the mistake. That's what you don't want to do. It's like, hey, if you're working with two other people and none of you are certain in how you're doing the problem, then stop there and get certain. It's almost comical, and I'm not looking at anybody in the room in particular, but you guys, it's pretty obvious who you sit with and who you might work with. It's pretty obvious. I can look at a paper from one individual, and if it's messed up, I can almost be assured the person they're sitting with did the exact same mistake. Why? Because you worked together and you made the same mistake. The hope is that by this point in time with the final, that you're not doing that you're like, if you're not confident, then reach out and get the confidence you need versus, we'll all through the problem the same way and hope for the best. Don't do that. You're just not doing the right thing. Did that answer your question though? Good, and thank you again for asking that question. Any other questions, anybody? Anything at all? Yeah? What do you think?
The third problem is a friction problem?
Yeah, and yeah, thank you for that question too. Sometimes the questions like that one right there is like, I could just stop with yes, right? But it jogs a memory. For me, it jogs something that I want to share with you. So the question, that's why I'm always encouraging you guys, ask questions, because sometimes your question, you might think, oh, this is such a minor question, but it jogs an important thing for me, right? The important thing for me is this: the friction problem. I want you all to trust me on the friction problem when I say this, because that's one I have written already. So there's 6 problems I've written. A couple of them I haven't figured out the other ones yet. All right, but I have done the friction problem. I guarantee you all that some of you are going to have a problem with the friction problem because you are going to not be able to convince yourself it's that easy. So trust the process, because that's what I'm looking for, by the way. I don't care if you got it right or wrong. I want to know, did you trust the process? Did you trust that if I just do a free body diagram and get that right and apply the equations of equilibrium, that I got an answer? And I'm confident in my free body, I'm confident in my equations of equilibrium. Trust me, if you do that, you're going to think, really, was it that easy? It is. But I guarantee you, even though I'm saying it right now, there's going to be somebody in here, and somebody in my 330 class that's going to F the whole problem up because they couldn't believe it was that easy. So thank you for that. I want to make sure you all heard that. In fact, I've got the centroid problem written too, or at least I think I do. Yeah, I remember that one now. I do. That one there, by the way, folks, the centroid problem is also a test of whether or not you dedicated yourself to believing in the idea that if I just draw that table the way that Dr. Hargrove did it on the board 19 times and just do what he did 19 times, then I'm going to be fine. That's all you got to think about. Just do what I did. Don't do anything special. Don't go down some road that's nothing like I taught, but just trust that process. If you do that with that centroid problem, easy. There's nothing to it. And then the third problem, of course, is the distributed load problem. I'm working on that one right now, folks, but I will promise you this. With the distributed load problem, it's going to be the same thing. Do you simply trust the process that I taught you here of how do I turn that distributed load into a point load? How do we do that? Where do I locate it? And then after that, it's going to be straightforward. But like I said, that one there I haven't quite worked out yet. I'm playing around with an idea. I want to see if it's going to work for the exam. But I promise you, just trusting in the process and showing that you trust in the process I've taught you is all I'm really looking for with that. What other questions might any of you have? Anything else, anybody? All right. Yes. Jen? Oh, super question. Honestly, if we were doing just those 3 problems in a room, it would be a 60-minute exam. And I promise you that if it's a 60-minute exam, and I'm only saying this because I've done this a million times before, where we actually did it in a room, I promise you, with those 3 problems, there would be people in the room right now that are walking out done in 20 minutes. And there would be some that would take the whole 60. But that's the way I would think about it. That's how long it should take you. It's a great question. Thank you. What other questions, guys? Anything, anybody? All right. Let's bring the course in for a landing. As we talked about throughout, I saved these last couple of days to talk about 3D statics. And before I do anything in 3D statics, I want you to know that the fundamentals of what we learned with 2D statics are not going to change one iota, not one bit. This is still, in 3D world, it's still about understanding how to write equations of equilibrium based on a free body diagram. And the free body diagram isn't going to be different at all, except it's going to be representing a 3D shape versus a 2D shape, that's all. But if we can apply the same principles to free body diagrams in 3D, where I've got a sketch of the object, I've got an axis system, I've got forces, where there used to be contact with something, that didn't change. If I've got a weight associated with this 3D object, guess what direction it's pointing? Straight down towards the center of the earth. Where's it passing through? Passing through the centroid. Nothing's changing here, folks, nothing at all, except now all of a sudden there's another dimension involved. So we're gonna have X, we're gonna have Y, we're gonna have Z. That's all. The only thing that's really different in 3D statics is we just have to get more entrenched in vector mathematics. That's all. Only in that case too, because it's easier. The vector mathematics, even though at first might be a little like, not sure I see how you're doing that, how you get that vector math. But once we have that part down, then it's like, oh wow, this is a lot easier. In fact, you'll see that today before we're done on a problem we saw a long time ago. So really, 3D statics is all about being able to work with forces, and of course dimensions, in 3 dimensions, and then working with forces in 3 dimensions using vector notation. That's it. Let's imagine here, let's take a look at an example of what if we had a force on a 3D axis system. And in a 3D axis system here, we draw these a number of different ways. One of the common ways you'll see in our book is to draw it like this, where you got the x-axis over here, the y-axis over here, the z-axis over here. And one thing about, notice no matter how we draw it, we're always going to follow the right-hand rule. Okay, folks, the right-hand rule of vector math being that in this case, if I point my fingers at the x-axis here and then I curl my fingers towards the y-axis, my thumb is going to be pointing in the direction of the z-axis. We want things to follow that general rule. So let's say I've got an axis system like that, and let's say that associated with that axis system, I've got some sort of a force. Now, I'm sure you all can imagine it's difficult to draw a force on a 2D whiteboard and represent what that looks like in 3D. But let's say I got some force coming up like this right here. So here's my force F, and that's going to be some sort of a vector force. In this particular case right here, it helps us to recognize what this might look like in 3 dimensions. So we can do a couple of things here. We could, for example, kind of show where this sits on the 3D, or the z-axis, how this sits on the y-axis, how that might come out. Let's see if this is maybe pointing out towards you guys, then maybe we represent that as something that looks like what you see right here, coming out, and let's see here, bring this down like so. Maybe down like this, and so on and so forth, until what we've got is this cube that kind of helps us visualize what does this thing really look like in 3D space. So in this particular instance right here, imagine this parallelogram that you see here that I'm sketching out with my finger as being representative of where this is on the YZ plane. Here we see this line suggesting that it's going backwards into the board with respect to this plane right here. And so again, I just did this to help visualize this, but even with all of that, we don't need, that's kind of a little bit of overkill. The thing that we need to understand is that just like we saw in 2-dimensional statics, when we had a force in 2D statics, so again, just go back to the good old days, X, Y, right? We had a force in the XY plane that was pointing off like I'm pointing right now. We know, and we've been doing this from day one, that we can resolve that force into its X components and its Y components, right? We know we can break that force down into its X component, its Y component. We know how to do that. Here in 3D world, at the end of the day, we need to do the same thing with a 3D vector, right? So the 3D vector here, this force that you see, is going to have some sort of force component along the x-axis. So in this case here, since this is pointing out, I just realized I drew that ever so slightly. I'm so good with it. Sorry. Head got messed up. By the way, that is that right there you just saw. It's one of the challenges of dealing with 3D and 2D. It's like so hard to sometimes visualize it. But think about this, folks. If I knew nothing more than an angle that this vector makes with respect to the x-axis, and I had some angle associated with that, let's say that that's theta sub x, then it's going to turn out that my force projected in the x direction, so force along the x-axis, which again, this is nothing more than the equivalent of the resolved force. So if this was 2D world, I'm saying I got a force, I want to know the x component of that force. We all know back then that if I had an angle defined between the x-axis and that force, that was going to be nothing more than the force times the cosine of theta, right? That was all it was going to be. Guess what? The x component here in 3D is going to be the magnitude of this force vector F here times, wait for it, the cosine of theta sub x. So if I know the angle that that force makes with respect to the x-axis, then I can write the x component just like that, no problem. So all right, what if I know the angle that this force makes with the y-axis? Let's see, I'm going to call that one theta sub y. Probably doesn't take a massive leap of faith to realize that in that case, the y component of the force is once again going to be the magnitude of F times, big surprise of the day here, cosine of theta sub y. And then lastly, of course, now, and by the way, just worth noting that there's nothing new in those two things right there. So in other words, if we had defined if this is 2D world, I got a force going off like this, and I want to know the projection of that force along the the y-axis. If I had an angle between the y-axis and that force, it would have been the force magnitude times the cosine of that angle. So nothing's new so far. All that's happening now is I've got a third angle going on here that identifies the location of that force with respect to the z-axis. So I got a theta sub z going on up here. And this goes without saying, the magnitude of the force projected along the z-axis would of course therefore be F times the cosine of theta z. So in all of that right there, and in everything I'm going to keep saying over and over again today, I want you to put everything in the perspective of what we already know with 2D stags. Now we're doing 3D stags, and we've expanded this just minimally. We already knew in 2D stags that we could project F along the x-axis, we could project F along the y-axis, and it was always the magnitude of the force times the cosine of theta between the force and that axis. That is nothing new. Here, we merely expand that to say, okay, in 3D, I'm going to crank this out in one more direction now, and it's going to be the magnitude of the force now multiplied by the cosine of the angle between that force and the axis itself. By the way, those three angles you see right there, folks, those three angles that you see, theta x, theta y, theta z. In 3D vector world, these are what's known as the directional cosines. The directional cosines, if you took each of those cosines and you found their combined magnitude, they would have a combined magnitude of 1. It's because of that the directional cosines are important in setting up a unit vector. And we're going to see that in just a hot second here. Just want you to kind of have that planted in your mind. In fact, we're going to find too that when it comes to identifying this force in vector notation, we're going to use vector mathematics or express that in vector notation, and in doing so, one of the many ways we've got to do that is to express the force as a combination of three magnitudes and the unit vector notation, which is going to be the directional cosine. So in other words, the vector F is going to be the magnitude of the force that's projected along the x-axis in the unit vector I direction. Now, that unit vector I, again, getting a little ahead of myself here, but I'll tell you, it's going to be the cosine of that angle. You'll also, in 3D though, we got to add in the other components. So this is going to be plus Fy in the unit vector J direction, plus Fz in the unit vector K direction. One of a couple of ways that we have to very quickly express a force as a vector. From this, it's also worth noting too that if I want to get the total magnitude, so as we note here, we've got this force, we're expressing it in vector notation, that's the bar, but what if I want to know the magnitude, or I want to relate something to the magnitude of the force vector itself? The magnitude of F turns out to therefore be the square root of Fx squared plus Fy squared. And by the way, folks, again, go back to good old 2D world. If this was a 2D situation, have we not seen a few thousand times that the magnitude of a force is nothing more than the square root of Fx squared plus Fy squared? We've seen that a million times, right? Now in 3D world, we extend that very simply to also include Fz squared now in that. So all of this said gives us a pretty reasonable, straightforward way of expressing, and this is a key thing I'm saying right now, expressing a force in 3 dimensions. As we're about to see, once we can express a force in 3 dimensions, then doing mathematical operations to it, the things that lead us to solutions to 3D stags problems, becomes pretty straightforward. So take, for example, if I wanted to add up forces in the x direction, would it be a surprise to say if I had all my forces expressed in 3D vector notation where I got an x component, a y component, a z component, would it be much of a surprise if I said, oh, we want to add up all the forces in the x direction, and all you do is add the x components of the forces together? It shouldn't be a surprise. If I want to know what the sum of the forces is in the y direction, I would just add up the y components of the forces. That's all we're doing here. But there is one thing that in the world of 3D statics, in the world of vector notation, that vector math brings to our table that makes something we've been doing even easier as long as we can do the vector math, and that is moments. If you go back and think about what we learned early in the course about moments, moments were the magnitude of a force times the distance from a moment center, any arbitrary moment center, to the line of action of that force such that that distance had to make a 90-degree angle. And when we first learned about moments, we did a few of those. And then we quickly saw, remember the good old basketball hoop problem? We quickly saw that there were going to be situations where figuring out what that distance was going to be a challenge. So we then embraced and learned the value of Varignon's theorem, where Varignon's theorem said to us, you don't have to worry about that distance, because if you can figure out an equivalent force system and use that equivalent force system to find the sum of the moments due to that equivalent system, then that sum of moments has to be the same as the moment that the original force would have created. We saw that in Varignon's theorem. We saw how that made the basketball hoop problem much easier for us. Still took a little bit of work, but it made it easier. But now here in the world of 3D statics, there's yet another method that once you get past the mathematics of the method, this gets really easy. Check it out. Before I leave this stuff here, because I'm going to need to create some whiteboard space here, folks. Does anybody have any questions about that? Anything here? I got to get rid of this for a while. All right, let me get rid of this. I might leave that up there for a moment. We may come back to that. It turns out I'm going to write it this way. In both 2D and 3D statics, it turns out that the moment can always be expressed as a vector. You'll see why we're talking about that as a vector in a minute, where that vector is going to be equal to the vector cross product of a vector that we're going to define in a moment called R. Now R is going to be what we're going to call a directional vector, and I'll get to that in just a hot second. Crossed with, so this is the vector cross product, the vector representation of the force F. And the mathematics on that goes like this. It turns out that this cross product is calculated by calculating a determinant of a 3D matrix. A 3D matrix that's going to have 3 rows, 3 columns. That 3D matrix, the first row, will always be nothing more than the I, J, K vector notation. That's it. That's the entirety of it. I'm going to skip the second row for a moment. The third row in this will always be the X component of the force, the Y component of the force, and the Z component of the force. The second row here, folks, I haven't filled in yet, will be the X, Y, and the Z components of the vector R. But we need to understand what R is first. So let me go back to this force that I've got drawn over here. We already know that we could express this force as, Fx in the I direction plus Fy in the J direction plus Fz in the K direction. We already know that. Let's say that I want to know the moment that this force creates about some arbitrary point. Let's say that that arbitrary point is like way up here in 3D world, and that arbitrary point has some x values, so there's some x value, some y value, and some z value. So even though, again, I'm drawing this out on a 2D whiteboard, imagine this point is just kind of floating anywhere here in space, and it's got, again, some x value, some y value, some z value to define where it is. It turns out that R, and this is an important thing I'm about to say here, R is defined as any vector that connects the moment center, in this case the point of interest, that connects the moment center with any place on the line of action of the force. So in other words, if I could construct a vector from this point here, we call this the moment center, let's call it point O, all right? If I could construct a vector to anywhere on the line of action of this force, it could be from here to there, here to the origin, it could be from here to here, it could be from here to here. Folks, it doesn't make a bit of difference, because remember, the line of action of this force I've got drawn up here right now, that line of action goes forever. It goes forever this way, it goes forever that way. So if I could even define a vector from the moment center to the line of action of the force down here, every one of these vectors, if I express every one of those vectors in unit vector I, J, K notation, no, I'm sorry, not unit vector, I should not have said unit vector, in vector notation, x direction, y direction, z direction, and put those terms in here. So I would have my second row of my matrix would be the x component of the r vector, the y component of the r vector, and the z component of the r vector. It turns out, and I can't stress the word any enough, it turns out that any choice you make for an r vector, whatever choice you make for the r vector, as long as it is a legitimate vector from the moment center to any place on the line of action of the force, it turns out this is going to give you the correct moment every time. The question, of course, becomes, how do I then calculate the determinant? Well, there's all sorts of ways we can calculate a determinant, folks, but the method I'm going to show you is the old school manual method. We can always plug in these in some sort of an app or something, get the determinant. That we can do. We at least should know how we do it. So the way we do it, folks, is when we're solving a determinant, at least in the case of a 3D matrix, and I'm taking this way up over here and starting up over here now, it turns out that determinant is going to be the following. Let me write it and then I'm going to talk about it just a little bit. So I just wrote out the manual calculation of the determinant of that 3D matrix right there. And it goes like this. The things you want to see here, folks, are there are going to be three terms in solving this. There's going to be a term for the vector, the unit vector I direction. There's going to be a term for the unit vector j direction. There's going to be a term for the unit vector k direction. What's important to notice here, folks, is this. Notice how the signs in front of each term alternate. We start with a positive. No matter what, we assume negative on the next term. We'll let the math straighten that out for us if it needs to. Positive, negative, positive. If this was a 4x4 matrix and we had a fourth term down here in our determinant, it would be positive, negative, and so on and so forth like that. You're always alternating terms. But for us, we're just dealing with 3D statics. We don't care about anything beyond 3 dimensions. So this becomes the equation that solves this. Now, this is something you might remember. You might find a way to store it so you can remember it, or there's another way to know how it's determined, and it's this. For the I term, the way these terms work is if you go back to your original matrix right here, if you're trying to figure out what the I term is, you're going to cover up, just imagine covering up the row that I is in and the column that I is in. So if I covered up this leftmost column in the top row, these four terms are the only things that I have left. The cross product is determined when you multiply this term by that term and subtract from it this term times that term. So RYFZ minus RZFY, and you see it right here. RYFZ minus RZFY in the unit vector I direction. From that, we would then we'd move on to the term that involves the J direction. So again, imagine you're covering up the row that J is in, and you're covering up the column that J is in. Now you're left with just these two terms that are not covered up, and if you do the same thing, product of RZFZ minus, I'm sorry, I said RZ, product of RXFZ minus RZFX, and you see exactly that right here. RXFZ minus RZFX. That's the unit vector J direction. Take a wild stab where the other one comes from. For the unit vector K direction, we're covering up the top row again. Now the rightmost column. Now I'm left with just these four terms right here. RXFY minus RYFX. Boom. There it is. So this is not something arbitrary. There wasn't any wild guessing on that. It actually comes from a process, and that's the process that you have right here. But that right there is the math that gives you that determinant. Now it's important to understand that the outcome of this process right here is going to be a vector. So that vector is going to have magnitude. Remember, folks, for every moment that we ever calculated in the 2D world, all we ever cared about was the magnitude, right? What's the moment that this force creates about point whatever, right? We only cared about the magnitude, but you're gonna remember something I said a long time ago about moments, and that is, there is no such thing as a moment about a point, about a dot. Moments, like torques, are axial phenomena. In other words, they rotate about an axis, all right? So if I had said, hey, I got a force here, and I want to know the moment that creates about this point right here, there was never any such thing about that moment making a rotation about that point. We were ignoring the fact that that point was actually on the z-axis coming out the board at you. We blew that off because we were in 2D statics. But what's happening in reality is that axis coming out the board here and that force are causing rotation about that axis. It's an axial phenomenon. What this method gives us here is it tells us not only what the magnitude of the force can be, because we can calculate that magnitude. We saw that earlier, I've erased it now, but we can calculate the magnitude by taking the square root of this term squared plus that term squared plus that term squared. We get the magnitude of the moment all day long, no problem. But what also comes out of this is, because of the vector notation, we know the axis about which that moment rotates. Powerful method. Let's see it in action. Recall some time ago, we had problem 242, which is, I put this up on the board, I'm sure you're going to remember it immediately. It was the trailer hitch problem. It was one of the early examples of us looking at Varignon's theorem. A pretty simple little setup here. Let me draw it one more time so we've got it all up here, folks. Stand by. Okay. Way back in chapter 2, we saw this problem here. The narrative went like this: as a trailer is towed in the forward direction, the force F equals 120 pounds is applied as shown to the ball of the trailer hitch. Determine the moment of this force about point O. So there was it was actually this point right here. We call this one point O. We need to know the moment of this. Now, for what we did back then, we resolved the 120-pound force into its x and y components, and we used Brignon's theorem to find what the moment was on that. But I want to do this exact same problem here using this methodology right here. I want to find the moment that this force causes about point O using the technique we've just learned here. So it begins with we need to turn that 120-pound force into a vector notation, right? So I showed you a few minutes ago that one way to do that is to write that out as the x component of the force, the y component of the force, the z component of the force, all in the unit vector I direction, and the unit vector notation is accomplished when we multiply by the directional cosines. That's a way to do it. There's an easier way. In this case here, if I resolve this force, just like we've done all along here, folks, if I resolve this force into its x and its y components, I slide this force down. I know I can anchor it right here in the center of the ball because I use that because I got some dimensions right there. Then I know that that force can be represented as a y component and an x component. Again, you got to imagine sliding this force down so it's right where my pen is right now. And I can convert this into its x component, its y component, and I know that this component right here was the force times, in this case, well, it would be the sine of the 30-degree angle. So 120 sine 30, which is equal then to minus 60. So I know what that would be. I know that this piece right here, and by the way, just to be crystal clear, we are assuming this is standard x, y coordinate axis system here, but. Now we have a z-axis and it's coming around the board at you. How do we know that? Remember, right-hand rule. Point fingers towards x, curl towards y, thumb is pointing in the positive z direction. So right now, folks, the z-axis, the positive z-axis is coming out and pointing at you. Now with that said, again, this force right here kind of deviated. That force right there would be 120 times cosine of 30. And since it's going in the negative direction, that too would be, that'd become minus 103.9, about 0.992, somewhere in that ballpark. Probably good at that. And we've known from all the way back then that once we convert a force into its equivalent, then we can get rid of the original force. We don't need that anymore. But what I just did right there, ladies and gentlemen, is absolutely nothing new. There's absolutely nothing in that that you haven't seen already. But it is from that, though, that we can very readily write the force F in vector notation. If you think about this, the force F in vector notation would be accomplished by having an x component which is going in which has a magnitude of negative 60 going in the unit vector I direction, and has a magnitude of negative 103.9 going in the j direction. And very importantly here, folks, there was no component of that force that was moving anywhere in the z direction, right? This was 2D, so there's nothing happening in the z direction, so simply plus 0 z. And there's my force vector. And by the way, it should not be a bit of a surprise that if we took 60 and squared it, added 103.9 squared, added 0 squared, and took the square root of that, wouldn't be a bit of a surprise that we would get back to the original force of 120 pounds, magnitude 120 pounds. But here now, folks, is where this gets interesting. I want to go backwards. I want to get rid of what I just did right here. Not that there's anything wrong with it. I just don't want to muck up what I'm about to show you here. So now I want to go back to the original force, which was, again, 120 pounds. on a 30-degree angle with the y-axis. What we just did a second ago was merely convert this into its vector notation. But I want to know now the moment that that force creates about point O. That was the ask. That was the original ask, right? So if I'm going to use this method right here, where I can calculate the moment using the vector cross product, where moment is equal to r cross f, and I know how to write the matrix out for that. My matrix is always going to start with ijk top row. That's never ever going to change. Down here in my next row, I would have those three numbers you see up there. I'd have a negative 60, a negative 103.9, and a 0 sitting right here. But I got that r vector, right? But we got through saying a second ago that the r vector, very importantly, the r vector is any vector that takes me from my moment center to any place on the line of action of my force. My force, as we've talked about so many times earlier in the course, its line of action goes forever along, the line of action goes forever, that way and that way, line of action goes on and on, right? I just need to find a vector that will take me from here to any place on the line of action of this force. Any vector. In this case, since the force line of action passes through the center of the ball, wouldn't it be true to say that a legitimate r vector would take me from the moment center to that point right there? And wouldn't it also be true to say that, well, to get there, I just need to go negative 11 in the I direction. Why negative? Because I said positives that way. So if I want to go from here to here, I need to go negative 11 in the x direction. And then from here, I need to go up 1.5 in the j direction. So a legit r vector would be negative 11i plus 1.5j, and that vector doesn't need to come out of the board or into the board at all, because there is no z component here. So again, plus 0z. That directional vector, this is what we call the r vector, the directional vector, is merely a roadmap for how to get from the moment center to any place on the line of action of that force. I go from here to here by going negative 11i plus 1.5j, and I get there. Yes, fire away.
Would it be a K for instance, Z?
Yes, of course it would. Thank you. Thank you. I don't know why I went and had that little brain fart right there, folks. But thank you for pointing that out. That would be a K. By the way, I do that all the time because I equate K's and Z's, right? So thank you for pointing out. Yes.
What does K, J, and I stand for? Like, why do we use those values instead of
Sure.
Z?
Aren't they unit vectors or?
They're unit vectors.
Okay.
So let me go back and draw real quickly here. Let's say I got an X, Y, Z direction. And let's say that I've got some force coming away from here that has a magnitude, a known magnitude of 1, right? The IJK notation would be the projection of this vector with a magnitude of 1. Its projection along the x-axis would be its I component. Its projection along the y-axis would be its j component. And its projection up along the z-axis would be its k component. So we just use IJK to be, I'm trying to think of the right word for this. We use IJK to be commensurate with I represents a direction or a unit, the length of the unit vector in the x direction, but we use I to differentiate the two. J is the direction, or the unit direction in the y direction, and K is the unit in the z direction. Does that help?
Yeah.
Sweet. Great questions, by the way, folks, and great clarity, thank you. What other questions might you guys have so far? So now we're gonna check it out and see how this all comes together. So now, and again, look at that R vector right there. Look at that R vector. that R vector, we merely used the dimensions of the original problem to write that out. We hardly had to think about it. It's just, okay, how do I get from point A to point B? It's like doing a Google map, right? It's really all there is to it. But was it the only R vector? Absolutely not. If I somehow knew, for example, where that point was right there on the line of action, then I could have said, well, I would go, I don't know, I'm just kind of making this up when I say this, -6 plus 10 or something like that to get to a point on that vector. And if I use that R vector in this mathematical construct right here, folks, believe it or not, you're going to get the same answer no matter what. This is the beauty of this method. It doesn't force us to have one specific way of specifying the directional vector, which means we can usually leverage dimensions to make life really easy. Now though, let's plug it into the math over here. So I want to do the vectors, so I'm going to do R cross F, which we already know is the determinant now of the following matrix. We'll have I, J, K, and in my second row, the components on R, so -11 plus 1.50. Now in the third row, the components on F, so -60 minus 103.90. And I know that that determinant is going to be calculated by using that equation over there, but again, even without the equation, cover up this column, cover up this row, because we're covering up the column in the row that I is in. So I'd have 1.5 times 0, 1.5 times 0, minus 103.9 times 0, that whole quantity in the unit vector I direction. So that term you all see right there is the same as this term right here. From that, I'm going to subtract. In other words, I'm starting with assumption of positive, now negative, and now my next term. So now I'm covering up the column that J is in, the row that J is in. So the only thing exposed is this -11 and the 0, the -60 and that 0. So I'm going to have -11 times 0 minus 60 times 0. That term right there in the unit vector J direction. And then my third term, we're alternating, so plus, minus, plus now. My third term, I'm covering up the row that K is in and the column that K is in, which is good news because finally I'm going to get something non-zero now, right? I'm covering up these zeros. So I'm going to have -11 times negative 103.9. So -11 times -103.9 minus, what do we have here? Minus -60 times 1.5. And all of that is going to be in the unit vector K direction. And folks, just look at this term right here. 0 minus 0 is 0. So this term simply becomes 0. 0 minus 0 here, also 0. The only non-zero term I've got is that 1 down there at the bottom. And folks, when I crank that all out, -11 times -103, that becomes a positive, minus the minus here makes it all positive too. When I crank this whole thing out, my final answer becomes 1,233.1, we'll just leave it at 1233, in the unit vector K direction. And that, by the way, folks, units-wise, we did everything in inch pounds, so this would be in inch pounds, which we all know from what we did back in chapter 2. We could divide that by 12 and get that down to foot pounds, which if we did that, that'd be about the same as 102.8 in the unit vector K direction, foot pounds. And folks, without going back and revisiting notes from all the way back in chapter 2, you may or you may not remember that these were the exact numbers we got back then too. Our calculation using Varignon's theorem told us that the magnitude of that moment was 1,233 inch-pounds, or we divided by 12 and got 102.8 inch-pounds. That's what we got back then. Today, we got one other additional piece of information. Notice, 102.8 foot-pounds in the rotating around the positive K axis. So we said that X, Y, the positive Z direction, which coincides with positive K, was coming out the board at you like this, right? Coming out the board. That's telling you that this moment here is causing rotation about point O, where the axis of that rotation is the K-axis coming out the board at you. We're rotating about the K-axis. But perhaps even more importantly yet, did you notice that it came out positive? Positive tells us that that rotation about the K-axis coming out the board at you is rotating in a counterclockwise sense. Remember the right-hand rule that I said a few moments ago, pointing my fingers towards X, curling towards Y? Define the positive Z-axis. Look at the direction of the curl of my fingers. It's counterclockwise. That's why counterclockwise has always been our convention for the positive moment. The math here just forced that to be true. So just in doing this right here, now we can expand our answer and say, yep, I know the magnitude of the moment, I know its directionality, and the fact that it came out positive means I know it's clockwise about that moment, or about that axis. And we got the exact same thing. The difference here being that we didn't have to figure out Varignon theorem or anything like that. We just plugged in the force. We knew it in vector notation. We plugged in any old R vector and nailed this thing. I promise you folks, if we put in a different R vector, like the one I hypothesized, what if we knew something up here, it's like -6 + 10, something like that. I promise you if we put that in into our matrix, we would have got the exact same answer. What questions might you have on what you just saw right there, folks? Nothing. I want to do one fast version of this, a 3D version of this, folks, just so we can see it. Actually, do I want to do this right now? No, actually, folks, I think I'm going to stop here, so I want to have time to talk with anybody that wants to talk here. Let's stop here. When we get together again on Monday, I'm going to show you a 3D version of that just to cement this home, or cement this in, and then we'll also see one 3D equilibrium problem. We're going to call it good at that. Have a great rest of the day, folks.